Hi, my name is Tae Lee, and this is our Advanced Machine Learning project presentation. We are Tae Lee, Minjik Kim, Hanor Jung, and Cheong Son, and we worked on the designing and implementing different CNN models to achieve emotion recognition. First, I would briefly like to introduce our project, and then we'll take a look at some CNN models and their analysis, YOLO model, and our final result. After four of us became a team, our number one priority was choosing the perfect project topic. However, it was not easy considering our technical background and knowledge. So we set two standards in choosing the right topic. First question, could we implement it? It is obviously clear that the project should not to be easy, but it also had to be challenging to a certain extent. Second, there had to be a data set that we could use, or it at least should be possible for us to make the data set ourselves. After choosing this criteria, our team could finally choose the topic, emotion classification and recognition. For the project, we decided to implement the existing models ourselves. Meanwhile, we find ourselves a PPT slide from the lecture note. From this PPT slide, we chose four models: ShallowNet, Google, AlexNet, GoogleNet, and ResNet. Our team wanted to find out what contributed to the result of reducing error rates in the graph, and above all, we wanted to implement the CNN model that we learned with our own hands. So from now on, I would like to take a look at the results, our very own ShallowNet, AlexNet, GoogleNet, and ResNet. For the dataset, we use FER 2013. This dataset comes in a CSV file and has seven labels: anger, disgust, fear, happy, sad, surprise, and neutral. The dataset can be converted into 48 by 48 pixel size of grayscale images of different faces with different emotions. For pre-processing, we rescale the pixels by dividing them by 255. Next, we convert the labels from label encoding to one hot encoding. Lastly, we reshape the images into 48 by 48. We use Google Colab as our development environment, using the provided GPU as hardware. Also, we use NumPy, Keras, Pandas, Matplotlib, OpenCV, YOLO, and Flask. Now, let's take a look at the models that each one of us have implemented ourselves. First model that we have implemented is the ShallowNet. Here are the results. As shown in the first picture, the model showed a train accuracy of 97.85% and a validation accuracy of 47.28, which is a clear sign of overfitting. To solve this overfitting, we applied L2 normalization, but the train accuracy has degraded as well. So we added a max pooling layer, and by adding it, we could see that the validation accuracy increased to 50.6%. We also applied drawdown and increased epoch to 50, and it resulted in a better result, which was 50.74%. However, it was impossible to develop more than this due to the shallow structure. The second model we implemented is the AlexNet. AlexNet is the best model to modify the hyperparameters and check the results because not only the model is not too small, allowing the performance improvement to be visible, but also is not too large, making the model easy to learn. So we analyzed the accuracy improvement through various hyperparameter adjustments. In addition to changing the hyperparameters, to augment the data, we have flipped the data. This showed a 2.5% improvement in accuracy. So in conclusion, with the data sets with data augmentation, we could obtain 63.9 accuracy with learning rate of 0.0005, batch size 256 and 30 epochs. Next model we have implemented is GoogleNet. GoogleNet is a model which uses a concept named Inception, which is used to efficiently extract features. Unlike the models described above, GoogleNet uses an auxiliary classifier to solve the vanishing gradient problem. As you can see, similar to other models, an overfitting could be spotted, where the training accuracy exceeded the validation accuracy more than 30%. To prevent overfitting, we changed hyperparameters as well, including epoch, learning rate, batch, and etc. However, due to model complexity occurred from using many layers and inception model, it was not easy to overcome the overfitting. Last model we have implemented is the ResNet. For ResNet, identity blocks and convolution blocks are needed. The identity block is the standard block used in ResNet, and the convolution block is a block used when the input and output dimensions don't match up. This is the code that we made with identity blocks and convolution blocks. The original ResNet input takes two 24 by 224 images with three color channels, but to adjust this shape to our grayscale dataset, we changed the input size to 48 by 48 and reduced the number of channels to 1. Here are the results. Original ResNets have no dropout layers. However, with the original one, the one on the left, as epochs increased, validation loss increased as well. To solve overfitting, we added dropout layers at the end of each identity blocks and convolution blocks. As you can see on the right, this resulted in lower validation loss and higher validation accuracy. However, even though we tried a lot of times with different hyperparameters, we could not get the validation accuracy higher than 0.65 and the average maintained on 0.6 to 0.62. All of our models that we have implemented have some common limitations. Most of our models have shown overfitting within the extent, and moreover, our accuracy could not get higher than 65%. So we analyzed the case in two different perspectives, dataset and implementation. First of all, dataset FER 2013 had data where the boundaries between classes are ambiguous. What I mean by this is that some data were not even easy for human eye to distinguish its emotion. We think this is because people make different expressions for the same emotion they feel in common. In addition to this, there was a difference in number of data for each emotion too. Second, we arrived into the conclusion that our model was not strong enough to distinguish the datasets and to narrow the gap between the accuracies of training data and validation data. So we tried the following things to enhance our project quality. First, to fix the problems regarding the dataset, we gathered other data from many different sources and cropped newly added data and augmented them. However, because the newly collected data had higher pixel values, the allowed capacity of GPU memory of Google Colab was exceeded. Because of this situation, we could not use the newly collected data. So our team decided to focus on changing the model. We developed a new model using several techniques that have led our previous four models into high accuracy. Moreover, after analyzing the results, we could find out that the simple structures such as AlexNet resulted in higher performance. This was because when training data resolution is too small and when the models are huge compared to the training data resolution, there is a possibility of vanishing gradients. After deciding the model structure, we augmented about 30,000 existing training data by flipping, rotating, and etc. to obtain about 140,000 input data. Finally, in order to further increase our accuracy, when the learning speed slowed down during training, we slowly reduced the learning rate. Based on the conditions that just mentioned, we kept on hyperparameter tuning, and after dozens of tries, a validation accuracy of 69.9% was obtained. The code and model structure of the current pages you're seeing right now are the final model that we have reached after many considerations. Here are here are the actual results we saw with our customized net model. As mentioned earlier, the validation accuracy of our model reached up to 69.9%. At the end of the training, you can see that the model predicts correctly with the real image. To test our model in real time, we used YOLO v3. YOLO is a real-time object detection system with Darknet 53 as its backbone network. It predicts bounding boxes from the image in the first hand and then predicts the class of each bounding box. It has 80 object classes in total, but since we had to predict human face expression, we only checked the first class person. With OpenCV, we could use system camera on laptop, and then we pre-processed the video and put into our CNN model. For our final result, we decided to create a website using our customized net model. The website detects facial expressions and recommends music that matches them. We used OpenCV camera and connected into web server using Flask. Let's watch the demonstration video. The first video is the emotion when I get surprised. As you can see, it says spread one surprise and I look surprised. Next video is when I get happy. The song recommendations change as I seem happy, right? Finally, here's when I get angry. And the songs change also. Thank you for watching our presentation, and here's Q&A.